Welcome to Module 203D on efficient gas-fired forced air heating systems. In the last module, we looked at a basic furnace and all the components that went together in order to heat a building. In this module, we're going to see how those components have been improved and how they are much more efficient at doing the same job. This module has three different objectives, and we're going to start with Objective 1 in order to describe the components that make up an efficient gas-fired forced air heating system. Furnaces have two broad categories. We have standard or mid-efficiency furnaces, and then we also have high-efficiency furnaces. And then they are further categorized by their efficiency ratings called the Annual Fuel Utilization Efficiency, or the AFUE rating. The AFUE rating refers to how well the appliance will convert the heat created by burning the gas into the heat used by the building itself. In the last module, we discussed standard furnaces which have an AFU rating of anywhere between 55% and 78%. In this module, we're going to be looking at two different types. First of all, we have mid-efficiency furnaces that have an AFUE of 80% to 83%, and then we have the high-efficiency condensing furnaces that have an AFUE of 90% to 98%. And these are also considered to be ENERGY STAR approved appliances. Furnace designs have changed dramatically over the years, and it's all about utilizing as much of that heat as possible that we get from burning our fuel. Standard and mid-efficiency units tend to lose a lot of heat up the exhaust flue, which will exhaust hot combustion gases that condense outside. And this is when we see that white plume of smoke over top of a building. With this type of design, the combustion gases will exit naturally due to convection. High-efficiency units are built to recover and utilize as much of that lost heat as they can, and they do this by allowing the exhaust gases to cool inside the heat exchanger. The cooler combustion gases are now exhausted through a Schedule 40 PVC pipe instead of a steel pipe. Since the gases are so much cooler, convection no longer works. Therefore, we also need to add in an exhaust fan. We also need to be aware that the internal cooling will create internal condensation, which will need drainage. The components inside my high-efficiency furnaces can be broken down into four main categories: combustion air components, burner assembly, fan blower assembly, and the electronic circuit board. We're going to start with the category of combustion air components and look at the heat exchanger. The job of the heat exchanger is to transfer heat from the combustion chamber to the circulating air chamber while still keeping the combustion air separate. Mid and high efficiency units have better conductive materials and a higher surface area that allows for more heat exchange. High efficiency units also have a secondary heat exchanger. This is called the condenser coil, and it draws heat from the exhausted gases. It's made from stainless steel in order to resist any corrosion from the condensation. As combustion air cools, condensation naturally occurs, and so therefore heat exchangers need to have a condensate drain line. And this drains the carbonic acid condensate, which is the water and CO2 mixture, and it consists of all the components found in a typical natural gas combustion exhaust. High efficiency units also require a combustion air blower. Since the heat exchanger design increases the air resistance, convection is no longer adequate in order to exhaust the gases. We need the combustion air blower to draw the combustion air and the gases across the burners and through the heat exchanger. There's two different designs that we can utilize. First, we can have the induced draft fan, which draws exhaust gases out and is found on top of the furnace. Or we can have the forced draft fan, which pushes the combustion air in and is found on the bottom of the furnace. The combustion air blower also acts as a system purge blower, which means it's removing explosive gases prior to and after ignition. In order to make the combustion air blower work, we need to include a combustion air prove switch. The combustion air prove switch is a safety shutdown device, and it confirms the operation of the combustion air blower. It is a normally open switch inside a pressure controller. There is a hose that attaches the switch to the combustion air chamber, which senses the air pressure. And when the fan creates suction, the switch will close. If the switch is left open, it will prevent the burner from firing. Another safety device we have is the high limit safety switch, which can either be a bimetal strip or a switch that is a normally closed switch. It operates the same as with standard furnaces. Mid-efficiency units have up to 3 different sensors, and they're factory set between 82 and 94 degrees. The primary limit control is located by the heat exchanger, and the secondary or auxiliary controls are located inside the blower compartment. Our next set of components that we're going to look at is our burner assembly, and we will start with the igniter. There are two different types of igniters that we typically use. The first one is called the direct spark igniter, or the DSI, which works something like a spark plug. This will produce up to 5,000 volts of electricity in order to make it spark, and it can be combined with a flame sensor. The other type we have is a hot surface igniter. And within the hot surface igniter, we also have two different styles. The first one is the intermittent pilot igniter, which works off a 120 volt operation and will heat up to 980 degrees Celsius. This only runs for a few seconds in order to light the pilot flame. Then the pilot flame will ignite the main burners. An alternative to this one is the hot surface ignition system, and these are much more common. The hot surface ignition system will ignite the burners directly and uses a ceramic resistance heater to do it. There is a flame sensor that will turn off the hot surface ignition system when the burners are lit. This igniter will heat up to 1,370 degrees. The flame sensor that is found in our ignition uses a process called flame rectification. It's interesting that flames are actually electrically conductive, so as long as there is a flame, we can have current flow, which allows the control board to sense when there is a flame or when there is not. The last safety device that we have in our burner assembly is the rollout limit control. A flame rollout is when the gases and flames exit the combustion chamber incorrectly, and is caused by a number of different things. Make sure you're going over the list on page 13 of your module. This results in the exhausted gases entering the living area instead of leaving out through the flue. There's a high temperature limit switch located at each end of the burner, and the job of this limit switch is to interrupt the burner control circuit when it detects a flame. It also has a manual reset button, so if there has been a flame detected at any point in time, we'd have to make sure the furnace is operating properly before we reset this button. The final two components that make up the burner assembly are the gas valve and the burners. Our next component category is the fan blower assembly, which consists of the blower motor, the blower wheel, and the blower housing. The blower drive motor, typically in an HE unit, will be a direct drive for better efficiency and lower maintenance. It can also be a multi-speed permanent split capacitor motor, also known as a PSC. This type of motor will have 3 different speeds. It will run on low speed continuously for circulation inside the area. It will run on medium speed for any heating modes, and it will run on high speed for any cooling modes with the air conditioner. Our last component is the electronic circuit board, which will replace most of the low voltage wiring inside the standard furnaces. The job of the ECB is to control and monitor all the different functions inside the furnace, and will include other components like HRV units. The electronic circuit board screw terminals are for the low voltage connection going up to the thermostat. The R terminal is for the power from the circuit board to the thermostat. W is the return path when the thermostat calls for heat. Y is the return path when the thermostat calls for cooling. The G is for fan control and will allow us to turn the fan on and off manually at the thermostat. The C is a common terminal, which is not found on all thermostats, but there's constant power found between R and C. Anytime that we need to replace the circuit board on a furnace, we need to make sure we have the correct one, because there are many different options available, and we must make sure it is also properly configured before the installation for each different application. Construction and design of high-efficiency furnaces results in a number of different benefits, each one helping with the efficiency of the unit. Make sure you're going through the module and familiarize yourself with all these different benefits. Something you should be aware of is that high-efficiency furnaces require annual and preventative maintenance in order to make sure they are working properly. This is an example of a maintenance checklist that the average high-efficiency furnace is going to require. Some of the maintenance needs to be done monthly, some of it biannually, some of it annually. But we need to make sure that we stay on top of it in order to enjoy the full duration of the lifespan of the unit itself. You have now reached the end of this objective. Review your module, complete the knowledge check, and then continue on to the next video.